So, welcome everybody to the next instalment of Shoreline Glaciers and Changing Sea Levels, Chapter 14. So let's go to the next topic here, which is sea level change. So we've already talked about some aspects of this in class. Let's look at this first slide here, which shows us a number of reconstructions of past sea level change from the Cretaceous period, about 120 million years ago in the Cenozoic era, to the present. Okay, so we're moving in terms of these shorelines. So for example, here we've got the Cretaceous moving along here, and to the northwest of these lines, then of course we've got land, and to the southeast in each of these cases, and out to the east we've got ocean at each of these periods. So 120 million years ago this was the current shoreline, and what was happening in the Cretaceous was the climate was relatively warm, so we had high sea level, much higher sea level than today, and we can see how much of the land and lower lying land is inundated by water. If we move progressively in time through the tertiary, or what's known as the Paleogene and the Neogene here, and then into the Pleistocene, here we have our record at about 35,000 BP, or before present. We basically can think of this about 35,000 years ago, and then to 18,000 years ago in the orange dotted line, which is about the maximum of the last ice age. And so we see here the maximum of the last ice age, we've got the lowest sea level change. Okay, so we've got almost a sequence here. There's up and downs as we go in time from 120 million years to 18,000 years ago, but we've got a basic trend in terms of high sea level moving to much lower sea level, and at this time of course a lot of the water was locked on land as ice. And then if we move from there to the present day, we've got our present shoreline, which has similarities as we see here to the reconstruction of 35,000 years ago. In terms of the actual heights at these particular times, we see the Cretaceous as much higher in the past, the sea levels much higher in the past, about 200 metres than current sea level, and for the Pleistocene at 18,000 years ago, so during the ice age, or the maximum of the last ice age, is about 125 metres lower than present sea level today. Okay, so let's move along, continuing to talk about the effects of sea level and sea level rising and lowering. And the first of these is to think about what happens if sea level rises relative to the land, producing what's known as a submergent coast. It's being submerged by water, and we move from our coast here to one which has been inundated with water, and we immediately see some features such as these rivers here, which have become flooded river valleys, okay, and hills here at the coastline. Some of these become islands, or high areas at the coastline become islands, and we've got some submerged bars and dune features and so forth further out as well. Okay, just to summarise, so we've got hills that may become islands in terms of a submergent coast, river valleys that may flood and produce quite irregular features known as embayments, and dunes and other coastal features may become offshore bars. And finally we've got barrier islands, as we've discussed in class today. So another good example of the result of moving from ice age conditions to the present, and how sea level rise has then dissected such features as bay mouth bars to produce barrier islands. So let's look at the opposite of this now. So we've now got an emergent coast. So what's happening if sea level falls, and what sort of features and processes are we going to expect as a result of that? So we can do the same thing again. So here we've got our emergent coast, and the aspects to consider here are firstly erosion. Water that's flowing overland, so water in rivers and streams and so forth, so overland flow, we might class all these different types of water together, incises more into the land itself. And the reason for this is because of the gradient between the final position of the ocean here and the position of rivers or land flow has increased. It's increased because, of course, its ultimate destination has lowered. Okay, so we get more incision. So there's a higher gradient. Rivers and streams cut down to reach their lower position, and of course this is all under the force of gravity as well. So other features we've got here. We talked about in class wave cut notches when we were talking about erosional landforms or erosional processes. We've got a notch here, so we could get notches and also marine terraces. So these are these wave cut platforms which are then exposed. Okay, so there's essentially a process of either uplift or, in this case, sea level falling and exposing such features. We've also got a reef here, so reefs which are of course once submerged with live coral communities. We've then got them exposed. And finally a sandbar, and this sandbar has been populated by coastal dunes, so it's a sort of a natural topography for which coastal dunes can then start to be emplaced by sand being blown off the beach further to the back here, and as we see it's also anchored by vegetation and produces a large dune field here. So to look at some examples in terms of characteristics of submergent coasts, firstly here we've got a flooded river valley. Okay, so flooded river valley, the classic example is Chesapeake Bay, and we can see the irregular shape of Chesapeake Bay here. Another good example are fjords. So these are valleys carved by glaciers which are then flooded. Okay, so they then become fjords. And finally we've got another nice example of barrier islands which are dissected. What about emergent coasts? In the first example here we're showing very clearly in this photograph, if I can get my mouse to work, very clearly the linear feature here. Okay, so the wave cut notch, which is of course indicating the level of past high sea stand or past high tide level, where the waves and the class were doing all their work to cut into this cliff face here. Now that's sitting up higher than current sea level when seas have receded. Again, got another example here of coral reefs. Sea level rising. We've also got the possibility of uplift. Okay, so tectonic volcanically active coastlines. We've talked about that possibility before, particularly where we're also seeing cliffs. And the final example here from California, we're seeing past wave cut platforms, and we've got a sequence of these wave cut platforms which are now marine terraces. Okay, so once these features are above current sea level, they're known as marine terraces. We can see these are way up there, several meters up, and these are kind of relic beaches, or also referred to as raised beaches in certain literature. A beautiful example from California, where we've also, of course, got tectonic processes occurring here. So we've got the San Andreas, but we've also got local uplift and compression along the San Andreas, causing these marine terrace features. So what about factors that affect sea level, or driving mechanisms which are producing changes in sea level? We started to mention some of these, and the one we've talked about a little bit before, mentioned in other topics as well, is glaciers. And again, just to talk about the important aspect here, is this is ice which is locked on land or trapped on land. So sea ice or icebergs and so forth, so ice which is actually floating in the sea, is part of the water budget and doesn't affect the sea level, whereas water which is taken out of the sea and solidified on land does affect sea level in this way. Okay, so we've got increase in glaciers is fall in sea level, less glaciers is rise in sea level here. The next example, which is not so intuitive, is the variation of sea level with spreading rate. If we have a slower spreading rates at mid-ocean ridges, then the ridge here, and the sphere in the ridge itself, is not as high, it's shallower, and it's also not as broad, and it's also cooler. With a faster spreading rate, we get the opposite of that. It's broader, it's higher, and it's hotter. And as a result, we're pushing up the crust in this case and increasing sea level. And relatively, this is down and lowering sea level. So we can actually have, even though we've got spreading occurring here, we can actually have lowering sea levels if we've got slow spreading rates. Okay, so slower seafloor spreading is dropping sea level, or equals drop in sea level. Faster spreading equals rise in sea level. And again, this is the broader part of the ridge, and it's hot and it's higher. The last example here is small variations in temperature, and this is like we have to consider the temperature of the atmosphere, temperature of the land, and temperature of the water, and their feedback mechanisms, interrelated mechanisms over a whole global climate. So small variations in temperature, if we have a large amount of water, and of course we've got a huge amount of water in our oceans, a small temperature change can cause changes in sea level, such as in the Cretaceous period that we've just talked about earlier on. Okay, so if we have cooler temperatures overall, then water contracts and we have a drop in sea level. If we have warmer temperatures overall, then it expands, water expands, and we have a rise in sea level. Okay, so these are our three main factors here. Of course, we talked about local factors in terms of storms and storm surges and so forth as well. Another factor to consider is the position of the continents and how they influence global sea level. And this is again or ties back to examples that we've looked at in class and discussed a little bit in class already, depending on where continents or supercontinents once were on the planet. So most of our continental masses today are at low to middle latitudes, but if we have a continental mass at a high latitude, then we can actually, of course, put more ice onto that continental mass. So we need land. That's the idea. We need land in the high latitude areas to actually get sufficient ice on there. And if there isn't any land, if our supercontinents at some time in the past were at low latitudes, then even with cold temperatures, we're not going to get such significant changes in sea level. So there's an important implication here about the position of continents and how the position of continents has moved around. You might remember the supercontinent of Rodinia 600 million years ago was centered on the South Pole. Okay, so that's a good example of where we would be taking out a lot of water from the oceans because we can put a lot of ice into the polar region there. Okay, the last slide of this particular section, how loading and unloading affect elevation. We've talked about loading and unloading and how we can load the crust if we have sufficient masses on it, such as putting mountains or something like this onto the crust, or building mountains on the crust. That loads the crust. If we think about significant accumulations of ice, and we're talking about here in terms of ice sheets, where we might have thicknesses on the order of several miles or miles to several miles, then these are a significant mass, of course, and they push down the crust. And when they push down the crust, they allow the seas to inundate it, as we show in this first figure here. The opposite of this, of course, is when we have glaciers melting away. So after the maximum of an ice age and everything melts away, then all that weight on the crust is released and it slowly unloads, it slowly flexes back up, so it's isostatically rebounding to get to an equilibrium position. And this particular process of unloading and rebounding is happening today, or is still happening today, as a consequence of the last ice age. And there's various parts of the world where this can be monitored or is being monitored, active uplift. One example here is northeast Canada, and this is a record of the last 6,000 years or so of rebounding. We see the sorts of amounts of rebound moving from 100 meters in the orange and yellow, perhaps moving down into the blues of 20 meters. So we see we've got some areas where this rebounding is occurring far more, okay, where we consider we've had far more weight on the crust, for example, which is going to rebound more, so it's going to flex up and isostatically equilibrate to a greater extent.